experiment. So what is carbon dioxide removal and why is it of interest now? The 6th IPCC assessment report, Working Group 3 report in fact, explains that carbon dioxide removal more generally, known as CDR, refers to deliberate human activities using technologies, practices and approaches that remove and durably store carbon dioxide from the atmosphere. Storage can be in vegetation on land, soils and in geological formations and in manufactured products, or, as in the subject here, in the ocean and in coastal marine environments. While some form of carbon dioxide removal is required to achieve global and national targets of net zero greenhouse gas emissions and to abate any residual fossil fuel emissions thereafter, it is not and should not be viewed as a substitute for the immediate and deep emissions reductions that are required now. However, CDR is part of all model scenarios that limit warming to 2 degrees centigrade or lower by 2100. CDR implementation will require decisions regarding CDR methods, scale and timing of deployment, and how sustainably and feasibly constraints can be managed. There are many different CDR methods and associated implementation options, each with different timescales and risk factors. Depending on scale, CDR methods could have co-benefits or indeed adverse side effects, which would need to be managed through appropriate CDR governance and policies. Implementation would also need to go hand in hand with robust and transparent monitoring, verification and reporting, or MRV. So the aim of this side event seeks to raise awareness of the increasing scientific, governmental and commercial interest in using marine environments to facilitate carbon dioxide removal. And this is known as MCDR, the M being for marine, as a means of supporting climate change mitigation efforts. Marine CDR offers some particular attractions. The ocean is already by far the largest sink of mobile carbon on Earth at about 37,000 gigatons of above ground inorganic carbon, 50 times more carbon in the ocean than in the atmosphere. And covering 70% of the Earth's surface, there is potential for at least some MCRD approaches to be implemented at scale. Moreover, CO2 could potentially be stored in the ocean with much longer durability, centuries to millennia, than land vegetation and soils, say. On the other hand, the marine environment is a complex system and possible ecological impacts are not well characterized. Unlike localized land-based CDR, the transboundary implications of marine CDR will present governance challenges. And the design of MRV in the ocean environment, where currents and mixing move materials around, will need considerable care in design. So to inform the debate and decisions, science has a key role to play in assessing the efficacy, durability, scalability of different approaches and evaluating ecosystem and downstream impacts and co-benefits and supporting the design of implementation of robust monitoring, reporting and verification. The objective of this side event is not to advocate for or against the use of the oceans in this manner, and nor does it aim to promote or discourage particular approaches. Instead, the aim is to provide a balanced representation of why there is interest in this sector, what scientific, commercial and governance aspects need to be addressed in order for any proposed approaches to be implemented. This side event has been proposed by, and several of the panel members are from, the CO2 CDR, or Strategies for Evaluation and Assessment of Ocean-Based Carbon Dioxide Removal, a project funded by Horizon Europe. And its aim is to unite the scientific, economic, legal, political, social and ethical researchers to develop the mechanisms, tools and guidelines required to ensure that ocean's CDR removal techniques can be evaluated and could be implemented in a responsible manner. As such, the event is being structured around the need to unite the key actors, and they are here today. So I'm now going to hand over to my co-chair for this session, Paul Holtus, who is the founding president and CEO of the World Ocean Council, the global blue economy business organization, who will make a presentation and introduce the other panelists. So, Paul, over to you.
Great, thanks, Ed, and thank you all for joining us here and online. We at the World Ocean Council are very happy to see this level of involvement of the ocean CDR issue at this COP. 3 years ago, we had proposed a formal side event on ocean carbon dioxide removal, and it was the only, there was just the one event at that time, but this is really now becoming a highly discussed and mainstream topic. So to look at the title of our session here, and we've been very happy to partner with the National Oceanography Center in the UK in organizing this, along with the other partners that are represented here on the panel and you see on the screen. And the title really reflects very clearly what the focus is here, and just reiterating a bit the stress that Ed put on this. The science of ocean sequestration of carbon, the governance, the policy, putting those implementing and enabling conditions together, I should say, and this, we've chosen these terms very carefully for safe and transparent carbon sequestration in the ocean, but also for implementation in the title, because we really do need to look at this as part of the toolkit, a part of one of the most important ways in which the ocean can be helping us address our climate crisis. So we have, along with Ed and myself here, we have Carrie Nichols from Ocean Visions, we have Ken Buesseler from the Woods Hole Oceanographic Institute, we have Eleni Houle from the Center for Climate Repair, and Shaun Fitzgerald from the Center for Climate Repair. And we will get into now some more specific presentations, starting with myself, to provide a briefing on this and across the sectors, in a sense, of what ocean carbon dioxide removal can and should be considering moving forward. And what I'm bringing to this then, putting on my World Ocean Council hat, is the interest and engagement and needs and opportunities from the business and investment community. The World Ocean Council is the global blue economy business and investment organization, and I'll mention a little bit more about that in a minute, but to really focus on the specifics of what this means for ocean carbon dioxide removal in terms of business, investment, and the role of the private sector. So to put it simply, to think about the supply, the demand, and the enabling conditions, particularly regarding, as Ed pointed out, monitoring, reporting, and verification. So on the supply side, there are a growing number of really smart and dedicated entrepreneurs who are putting together the companies that are working to understand and develop the possibilities for improving the ocean's ability to sequester carbon. And we are pulling those companies together to facilitate them evolving into possibly an industry association that will be what is needed here to ensure we've got standards of practice, we've got a common voice, there's a quality control system for the future of carbon sequestration in the ocean, and an exchange of best practices, et cetera, that allows that growing industry to engage best with other stakeholders, and particularly with the investment community. On the demand side, at the core of the World Ocean Council is a large and growing corporate responsibility community. And these companies from shipping, fishing, and other industries have the potential to help accelerate and jumpstart the ocean carbon sequestration relationships between buyers and sellers. And so we're working to engage those industries in that potential role as supporting the carbon market if and as it develops for ocean sequestration. But also on a practical level, many of the ocean industries have a role to play in implementing carbon sequestration. From the shipping industry, the port sector, the mining industry, depending on which different pathways that you'll hear more about that are developed for carbon sequestration, along with the data side in terms of technology, instrumentation, analysis, and this feeds into this point here of measurement. So monitoring, reporting, and verification. We need the tools, the instruments, the analysis to ensure that we understand, is the amount of carbon being sequestered actually occurring? Are there or are there not unanticipated, unacceptable environmental ecosystem impacts? And so the role of data and this MRV is a critical component to moving forward with this. So that's the core message here from my side, just a bit more to go into that a little bit more, and the background to this is the World Ocean Council, as I say, the only global organization pulling together the international multi-sectoral business and investment community that is based on the ocean, the use of ocean space and resources. We have a network of some 35,000 plus investors, corporates, individuals, industry associations, et cetera, focused on this potential and this need for leadership, coordination, and action from the business community. The sequestration side, in terms of the business community, as I say, it's the enterprises themselves, the investors or funders, and the marketplace that are coming together around both the blue carbon, but especially for our discussion here today, the ocean carbon sequestration community. And I won't go into this in a lot of detail because I know other speakers will cover this, the different pathways for which we can explore carbon sequestration, and you'll hear more about this. And the image and the list of these pathways, as we call them, comes from the National Academy of Sciences report that came out a year or so ago, or a couple of years ago now, that's really set the stage in defining this gigaton scale potential. And this is, from my side, if you remember nothing else from what I've said, it's what these numbers indicate. This is our nature-based solution, gigaton scale potential for the planet, and so we really need to explore this to see if there is really safe, transparent implementation of ocean CDR that can be taking place. As we work to engage the business and investment community, we're working to create, as I say, that pre-competitive collaboration from the enterprises, the other ocean industries, and the investment community, and bring that together to engage with the policymakers, governments, intergovernmental organizations, the science community, the environment community, and the public more at large, so that success really looks like this. Like we want to have this business and investment community organized and engaging on developing and advancing carbon sequestration in close partnership with governments, the international community, the science community in particular. And if there is a future for this, then we need to mobilize the investment behind it and the partnerships with the public sector so that we can move this forward. And underlying this, in the bottom line here, the last bullet, the science behind ocean carbon sequestration, so it can be done in a safe and transparent way. And this is the same slide as the beginning. Supply, demand, and the enabling conditions, particularly monitoring, reporting, and verification, is where we need to move with this in partnership with the sort of organizations and information and expertise you'll be hearing from now as we advance and explore this important potential. So with that, I will hand it over to Carrie to pick up the discussion from Ocean Vision. So Carrie.
Thank you, Paul. So my name is Carrie Nichols, and I am a Senior Program Officer at Ocean Visions. And I was asked to speak about a contribution that our organization, with the help of lots of input from many scientists, we put together this, what we're calling a high-level roadmap, which is a comprehensive program to either prove or disprove MCDR technologies by 2030. And it's really about leading with the science, what science is needed to either decide that it could be responsible, safe, and effective to move forward with the different pathways of marine CDR or not. Our organization is a nonprofit that's at the center of a robust network that's made up of oceanographic institutions, some private institutions, and other NGOs. And collectively, we catalyze collaboration for the co-design, development, testing, and evaluation of solutions to this interlocking ocean climate crisis, because we can't separate the ocean and the climate from this crisis. The ocean is a main player in the climate. The ocean has absorbed 90% of heat energy that has been caused because of climate change. And I want to point out here that some of the members of our panel are associated with institutions that are part of our network, including the National Oceanography Center, which just recently became a member of the network. So, the reason that we're even talking about carbon dioxide removal here is because, unfortunately, emissions reduction alone will not get the job done to get us where we need to be at a safe climate, especially to avoid some critical Earth systems tipping points. And so we need a more robust agenda to confront the climate emergency. So absolutely, we have to reduce, and I think that everybody here on this panel agrees with that we need to cut emissions, and we need to do so as quickly as possible. But that we also have to remove carbon dioxide. We're basically cleaning up carbon pollution that we've put into the atmosphere and into the ocean. And then in the meantime, we might also need to start thinking about repair. So are there ways to stabilize critical marine ecosystems while we're also doing this really critical work of reducing and removing? And maybe the most important R here is actually reach. So we have to build global capacity to innovate and develop ocean climate solutions. And it really needs to come, this is an all hands on deck situation where we really need everybody from everywhere thinking about these problems. So, as was mentioned earlier, all pathways that limit global warming to 1.5 degrees C with limited or no overshoot do require carbon dioxide removal on the order of 400 to 1,400 gigatons over the 21st century. And this is the IPCC report that this comes from. So how are we doing? This was a study that came out, the state of carbon dioxide removal, which was a global independent scientific assessment of CDR. The world is currently removing about 2 billion tons of carbon each year, almost entirely through conventional strategies like afforestation. But the report, and I think the IPCC report, point out, though, that we're going to need novel methods of CDR, such as some of the things that we're talking about here today. And this next decade is really crucial for novel CDR. This is from the report. Failure to create momentum in this formative phase will contribute to a widening gap by 2050 and beyond. So we really need to grow this field of novel CDR, but again, we need to make sure that the science is leading us. And we need to do so really, really quickly. These are the pathways that was also pointed out that are identified in that NASEM report, and I'm not going to go into the details of all of these different pathways, and I'm assuming that that's going to be covered by somebody else. So what Ocean Visions has done is we've tried to really focus attention on what the knowledge gaps and research priorities are to move this field forward. And so we created these digital roadmaps. These are living documents that get updated as new information becomes available. And we have one for each of these different CDR pathways, ocean-based CDR pathways. And then the ones in green are ones that are cross-cutting. So they have themes in it that relate to all of the different other pathways. And so this is a place where you can go if you're interested in learning more about some of these technologies and sort of where we're at and what needs to be answered in kind of a high level. And I want to point out that there were dozens of scientists, many, many scientists, open workshops that created to the generation of these roadmaps, and that are also, if any, this is also, as I mentioned, a living document. Anyone can go into these roadmaps and update them. But we're kind of at the point, so these roadmaps have been developed over the series of a couple years, but we're at this point now where we're trying to think of, well, how do all the pieces of the CDR puzzle fit together, and how can we really catalyze the next steps? We really need to know what are the absolute next steps that need to happen in order to make these, to really, get to the point where we can make a decision about these technologies. So this is that high-level roadmap that I mentioned, and it's really about making decisions by 2030, because that's at the point where we're going to need to be scaling up efforts and actually start to be thinking about implementation and deployment. This high-level roadmap was developed iteratively and again collaboratively. So it was developed by the Ocean Visions team, and then contributions were welcome from members of the leadership team that were associated with those different network partners. They, gave feedback and then moved forward. And importantly, this is only version 1.0, and it will be updated again as the other roadmaps are updated as well. And this is basically a high level of what needs to happen across all of the different pathways. For any given pathway, there also needs to be very, very detailed research frameworks, and I think Ken might speak to some of the research frameworks that have been developed for some specific pathways. So in the report, we identify these fundamental questions that must be answered in order to move forward, and there are some questions that have to be answered using controlled field trials, and so moving out of laboratory experiments to controlled field trials. So does the MCDR activity generate a measurable reduction in seawater carbon dioxide concentration? Can net additional ocean uptake of atmospheric carbon dioxide be tracked in response to the activity using a combination of sensors, platforms, and models? What are the impacts to marine ecosystems of MCDR activities, and are they acceptable when compared with the impacts of the no-action alternative or of other feasible mitigation measures? And what are the range of impacts to human populations, and are they acceptable when compared with the impacts of the no-action alternative or other feasible mitigation measures? There's also some really fundamental questions to scalability that don't require field trials. These include, what are the necessary materials for scaling an MCDR approach, and can they be sourced, transported, and delivered to key regions with acceptable cost and environmental impact? So, thinking about from a life cycle perspective. And then what is the required suite of technical, economic, social, and political enabling conditions that are required to permit growth of a given MCDR technology to the scale of gigatons of annual CDR, and what is needed to establish them? And the way to address these questions, and these questions I should also add are not hierarchical, they all need to be looked at the same time in parallel, especially since we don't have a lot of time. And so there's 3 pillars that feed into answering these questions, and again, to try to see, are these technologies deployable at climate-relevant scales? So science, we need controlled field trials, but there's also supporting lab and mesocosm studies that can be done. We really need to move on the MRV tools and the confidence in those measurements, and also thinking about having standards across the industry. Also, there needs to be a lot of social science that's done in thinking about the conditions of use. The next pillar is technology, so optimizing for scale and efficacy. So application of new technology, there's a lot of people from other fields that aren't engaged in marine CDR yet, and they might make really meaningful contributions to thinking about, the future of this field, the future of these technologies. It's really important to start doing some scaling analyses. So spatial suitability analyses are one. We're doing one with Esri right now, where we're looking at places in the world that might be the most meaningful and sort of most optimal conditions for doing ocean fertilization to grow microalgae, for example. Also, analyses thinking about co-products development. So some of the technologies have the ability to perhaps have co-products associated with them. And so what are those co-products? What does the scaling of that look like? And then also importantly, thinking about developing innovation hubs, so getting people together from different parts of the world, again, working on these problems together. And then the last pillar is policy. So what are the conducive enabling environments? We know increasing social and political salience, and then the creation of really supportive regulatory frameworks. So, especially here really we're talking about research. We are not talking about deployment. This is all about the research that's needed to prove or disprove some of these technologies. And so, getting to the point where we can do the research is going to be extremely important. And again, these pillars must advance together if we're going to make progress at the time scale needed. So it's not do the science, then do the policy. We need motion in all 3 of these pillars. So lastly, how much will it cost? So this National Academy study that was mentioned earlier estimated at about $1.4 billion. A later study estimated $2.1 billion, and then a more recent study, as we learn more and we also identify what the research questions are, realizing that, there's a lot of information that we need. And so this most recent price tag, and again, this is looking across all of the CDR, marine CDR technologies, estimated at $12 billion. So it's going to cost a lot. We're going to need public funding. And we're going to need, support again in making this research happen to really make this a critically important decision about whether or not to move forward with marine carbon dioxide removal. So there are links if you are interested in looking at our roadmaps of roadmaps. And thank you very much for having me, and I'll hand it over to Ken.
Great, thanks, Carrie. So Ken, over to you, and we'll just keep the ball rolling here. Thank you.
That's great. Thank you, Paul. Thank you for spending one of your last probably talks here and with us on a last day of this COP with full session. I'm kind of going to introduce some background and then get into ocean iron fertilization, one of the CDR techniques that we're going to get into a little more detail. That means 4 slides in this type of setting. But basically, we're going to ask this question, what can the ocean do to help with this climate crisis? I don't have to explain the climate crisis to this crowd. I think it's good to review this idea, and you've heard it from a couple people already, that the path forward, and I'm pretty optimistic that we know what we have to do, because we have to immediately reduce fossil fuel emissions. So that's the dark gray line there. Emissions reductions are part of all of this. And we know how to do that, right? This is a governance, this is a political decision, it's economics. But we can move down a path where, say, by mid-century, we could balance our emissions with these offsets, negative emissions, what we're calling here carbon dioxide removal. And you're going to hear about a few ways the oceans can do that. And so the scale of those two things, as you look out towards the end of the century, we need to be removing on the order of, say, 10 billion tons of CO2 per year. Right now, we're emitting on the order of 40. That's a big challenge. I think we can meet that. You're going to hear some ways to do that. But that's a big number. And I don't know about you, but when I try and think of billions, it's hard to know what that is. So I've been thinking of this train analogy of a coal car, a train carrying coal, and each of those coal-filled bins is about 15 meters long and holds 104 metric tons of carbon equivalent. So you need a train to pull 1 billion tons. How long would that be? Well, it would circle the equator 4 times. That's a pretty long train. You'd wait a long time to cross. So we've got a challenge, but I think we can meet that. I think that's worth keeping in mind. So I remain positive. I also think the oceans, and the reason we're here is to emphasize the oceans' role in this, is huge. And that's really not just because it covers 2/3 of the planet, but of all the carbon that's being cycled, by the vast majority sits in that ocean interior. These numbers on this chart are in gigatons, again, my billion-ton train, 37,000 in the ocean interior. Compare that to the atmosphere, it's about 50 times more. So we're trying to get it out of the atmosphere somewhere. We've got to look at that big circle there, the deep ocean. There's been a lot of land-based, nature-based solutions proposed, trees and things. You look at those numbers, and there's competition, of course, for use of land, for numbers of things like food in one particular. But basically, the oceans are storing about 15, 20 times more than all of the land plants and all of the active organic matter in soils. So that's really important. I'll point out here, we're not going to get it really into blue carbon very much, I don't think, but it's a small reservoir, very important to protect. Countries should be doing this. Mangroves, salt marshes, seagrasses. These are places for fisheries, habitat, tourism, flood relief, but they're not going to be a big dial on our climate. So let's look further out in the ocean at what it might do for us. Well, people have mentioned this several times. I was fortunate to be invited with a group of 12 people internationally to be part of a U.S. Academy's report. Unfortunately, the month was March of 2020 when this started, and so everything was done on Zoom. We spent a lot of hours on Zoom with about a dozen faces there, and I've just met some of these people in person for the first time at this meeting. But anyway, we were tasked, basically, you're given a task. Let's look at these 6 different technologies, other ways to do it, 6 different approaches, nature-based on the left, what we call the engineered solutions on the right. And when we say nature-based, they rely a lot on plants to take up CO2 during photosynthesis. That can happen with seaweed, macroalgae, and that can also happen, we have the example here, iron fertilization. You can enhance the growth of the microscopic plankton, the phytoplankton, and their ability to take up CO2. Now, a product of photosynthesis, if you remember, is oxygen. So one way to think of that scale, half of the oxygen on this planet, you breathe in, half of that oxygen is coming from the marine life, the marine plants. So it is very important in that respect, and also for carbon. The smaller, slightly smaller circle below, ocean tubes, that relates to bringing up nutrients from that big reservoir. It's just a hard thing to do because you'd have to recycle the carbon you bring up at the same time. Ecosystem recovery in the open ocean, that's what that other circle is. That would be great to do, 30 by 30. We know how to do some of those things, but it's hard to make a big difference. You could enhance carbon in the ocean by hundreds of millions of tons, but not get to the billion-ton range very easily, and it'd be hard to measure. We should do that as well. On the right, we're not going to spend as much time, but you can grind up minerals, rocks, and change the alkalinity, another word for the chemistry of the ocean, so that you can get higher uptake of CO2 through solubility pump, we call that. It's not plants, it's a physical chemical, Henry's law action, getting gas in the ocean by changing the chemistry. And you can do that by putting electricity and electrochemical techniques, but that takes a lot of fossil fuel-free energy that we just don't have right now. So the last part of this, small amounts of iron. Think of nutrients in your garden, nitrogen, phosphorus you might add. Iron turned out to be a limit for growth in many parts, not all of the ocean. It's very abundant on this planet, comes mostly from dust. But if you go, say, in the Southern Ocean, that's satellites at 60 south, the land there is covered in ice, right? So you're not getting a lot of dust. Very low iron. Those two jars, glass jars there show before and after when we deployed iron behind a ship. It turned into that big U-shaped thing there. We grew a lot of diatoms, that's a ketophorus chain-forming marine plant with a silica shell. And the really amazing thing about iron is it takes a very small amount, 1 ton of iron, they don't need very much, gave us 2,000 tons of carbon, about 8,000 tons CO2 equivalent leaving the surface ocean. That's a lot when you compare it to like the Iceland direct air capture project that got 1,000 tons and made headlines. So we were doing this 15, 20 years ago. Very successful, but we did not really go that much further in terms of the durability and scalability. How much is getting deep in the ocean? Super essential, because if you don't get out of the surface ocean, it's like growing a lawn and saying you're sequestering CO2. That grass dies in the winter, or you mow your lawn. It's not there very long. You got to go deeper in the ocean to have time scales for durability of centuries, millennia. We know those numbers pretty well. We don't know as well that carbon flow after slightly larger and longer deployments. We were only out there for 30 days. We did not capture this part of the biological carbon pump. So the last couple of slides, I just want to introduce an effort I've been involved in leading. We call ourselves EXOIS, Exploring Ocean Iron Solutions. That's this international group, about 25 institutions. We meet every month for the last year and a half or so, talk about all of the issues we would need to address to move the science forward, the science leading the way. The QR code is to a document just over a month old, came out of it. Our first in-person workshop, 35 people. We took a week. We talked about durability. We talked about scaling. We talked about how you'd measure, even know about the intended and unintended ecological impact. We talked about costs. And then my last slide I'll leave you with is the ethical standards. How do we do this in an open, transparent, ethical way? So that document is available for anyone who wants it. And see me later if you don't have a chance to copy this QR code. But I think, before we really focus in on the science, the first thing we did with assistance from Margret Leinen, head of Scripps Institution of Oceanography, was really look at the conduct you'd want to have. These are called codes of conduct. There's several out there. But in our case, it really distilled down to making sure, first and foremost, why are we doing this? We're not a company. We're not looking to make money. We want to do something that would benefit humans and the environment. We want to set up how that would be done in a responsible way. So who would be responsible for even permitting this type of research is important to address, do in a way we would basically be following some of the international protocols set up under the London Convention, London Protocols. We commit to open research. That's what scientists do, peer review. We perform iterative assessments. You can't just do this once. We would do it in different locations to look at differences in seasonality and different growth patterns. That's very important. And we certainly have to do a better job maybe than 15, 20 years ago of bringing the public in on the discussion, telling them why we need CDR in the first place, what are the benefits, and basically, what are these no-go, no-go decisions? Because it can't just be left up to the commercial field to go out and say, we'll do this as soon as we can make $1. We have to really do this in the proper way. So with that, I'll pass it on.
Great, thanks, Ken. So moving on to Eline. So please go ahead and introduce yourself.
Hi, my name is Alil. I'm a researcher at the University of Cambridge. I look at the ways climate policies and negotiations often leave communities and countries behind, particularly developing countries or least developed countries. And today what I want to talk about is the whole area of ocean carbon capture is just so exciting, and there's really an immense lot of potential to not only capture carbon and GHGs, but also to provide benefits to countries who are developing, who rely on these types of ocean resources. So in today's talk, I'd also like to highlight some ways in which the type of development that can be developed can go alongside, the type of development that occurs in these left-behind countries can go alongside the technological development that we're talking about with my fellow panelists. I'd like to first start by re-highlighting this diagram that was published by IPCC's Working Group 6. It talks about some of the impacts that the ocean's role in carbon and GHG absorption is having. As the ocean draws in GHGs, it increases its alkalinity. As it absorbs heat from the atmosphere, it gets a little bit hotter. And these roles that the ocean is playing, which is really the biggest role any ecosystem has on the planet, is having really big impacts on the way the Earth operates. That includes melting sea ice. It includes having more intense and less predictable catastrophic events along coastlines. It also includes the destruction of or the change of biological life within the ocean. Those that arguably are most affected by these changes are the communities that have the least capacity to defend themselves against the impacts of these changes. So oftentimes you see coastal communities suffering because the fish that they've traditionally harvested have disappeared. They've migrated to warmer areas or cooler areas, in whichever it may be. You also see that their life is threatened by some of the natural disasters that occur as the sea heats up, and then you see like more intense cyclones and typhoons along these coastal regions. Consequently, it's really important to understand how the ocean's role in absorbing carbon and other GHGs should be managed and, let's say, mitigated in order to reduce the effects of these impacts on these vulnerable communities. And that's a role that we should consider as we develop technologies to enhance the role of the ocean in climate change mitigation. Part of my diagram is missing, as often happens. But essentially, when we look at the role of technology in developing countries, we can look at it from two perspectives. One is, how does development occur in relation to the technology that's being developed? And the second is, how is technology developed in relation to the developing context in which the technology will be applied? In this first slide, we see that when development occurs, there are three really major factors that we want to consider. The first is policy. We want to look at finance, and finally, we want to look at technology. When we're talking about policy, we're looking at the environment, the institutional environment within that developing country. It could be formal in terms of law or actual policies that are published by the government. It could also include informal policies or rules or codes of conduct that people generally tend to follow when they're part of a society. These could be religious, spiritual, or just gender-based, anything. And it's important to consider that type of formal and informal framework because we want to make sure the technologies we're developing are aligned to the values of that society. When we have a good correlation between the technology's benefits that they produce and the types of values that are adhered to in a society, we find that technology is quickly taken up. We also want to see like the financial capability or capacity of that country or the environment around the country in terms of development. And so that could include both the budget of a country. It could also include UNFCCC financing that flows through different financing mechanisms. And it could also look at the private sector. And this is important because countries need to be able to afford and buy, implement, manage, scale up the technologies that we can develop for climate change. And finally, we want to see the technology itself, whether it's developed, and as we'll look at in the next slide, whether the technology itself has been built fit for purpose. If you have an imbalance in any one of these three areas, you find that technology often grows at a rate faster than can actually be adopted by the environment. So if you have technologies that don't fit into the policy, you don't really have an environment to take up or make it affordable or feasible within that environment. And we see this often with solar paneling, where we have markets flood with solar panel technologies in developing countries, but we don't have the money in, at the household level to purchase it, or at the government level to scale it. And that ties to finance as well, because often policy and finance are tied together. But in the case of finance, we do see that oftentimes these technologies are financed by the UN, and then we need to see if, even if it's financed, is it in an environment that's suitable for its uptake? We also, and so as I mentioned earlier, the second area in which we can look at technology is technology in relation to the country's context. In this case, we can sort of measure the feasibility of a technology along 5 different points of consideration. The first being the capability of the technology to provide actual benefits to the country that's being implemented in. And these types of capabilities can be intended, such as the sequestration of carbon. It can also be a side effect. And that could be that you're improving livelihoods, or you're strengthening the resilience of the coastline so people are less impacted by natural disasters, for instance. Then we need to look at complexity. And here again, we can look at the level of complexity needed to manage, implement, and scale up a technology. Some technologies are incredibly simple, such as a smartphone. You don't really need to have a specific type of skill to adopt it, to buy it and then find value in it. Even if it's just to look at Instagram, or whether it's something more complex like reading a really difficult article online and then finding the resources to translate that to something you understand. So if it doesn't have too much complexity, it can be easily adopted. But on the other hand, you have technologies that are of vast complexity, in which case you need to develop an entire skilled labor force around it, include all the supporting infrastructure and technologies to manage it, fix any holes in it, and then, of course, in the long run, scale it up. We then look at compatibility, as I said previously, in terms of local values or the way people relate to technologies, and that type of compatibility is really important to making sure that technology is understood and accepted by that community. Fourth, we can look at the cost. So this is in terms of cost-benefit, whether the benefits provided are in line with the cost of the technology itself. And it also includes the actual real cost of a piece of technology, in which case you need to consider budgetary restrictions and other types of financial issues that come along with purchasing and managing technologies. And finally, we look at congruence. And this is different in a sense to compatibility, because where compatibility with local values is slightly flexible or elastic and based on time and space, congruence with local policies and markets is really important, because some aspects are inflexible, such as legal frameworks. In that sense, it also needs to be that the technology is really well matched to the policy and market conditions that exist. Alongside this, technologies can also be developed in terms of people-centrism or market-centrism. Oftentimes in the Western world, we find that technologies are developed looking at a market. Is there a need? Is there a demand? Can I provide a technology to fit that gap? But in the developing world, we also want to make sure that these technologies have people-centrism, in the sense that, are they providing positive benefits? Are they acceptable to the values of the people who will be interacting with it? And then so there's a spectrum there as well. I'm just slightly worried about going over time, so I'll rush. But here's an example of an ocean-based CDR method that is being rapidly scaled up in developing countries. On the left, we have coastal mangroves, and on the right, we have sea kelp. These are both very people-centric forms of MCDR, and they're people-centric because people recognize them. Mangroves have spiritual and cultural values to coastal communities, and this allows these types of MCDR methods to be understood and relatable to communities, and which is why it's often the most popular and most easily adopted form of MCDR in developing countries. The map on the left kind of shows you that it doesn't have to be one type of solution or one type of kelp that's adopted, but rather depending on the location and people's nutritional needs or appetite for what they would want to eat, you can have a wide range of different macroalgae adopted in those areas. And then I just finally want to look at gaps in climate financing. If you see the way UNFCCC is financing flows to developing countries, the vast majority of it is towards mitigation and adaptation. These efforts are regionalized and localized. You'd have to be a country or an organization to apply for these fundings. And what that means is that the efforts to repair the environment through these funds is also very fragmented. And it depends on the capacity of that specific local area to access these funds as well. Now, adaptation generally, of course, I don't need to really explain it to this crowd, but just in case, adaptation generally refers to the adjustments in ecological, social, or economic systems in response to actual expected climate threats. And this helps people change their behaviors to reduce their long-term risks to those changes. Mitigation refers to efforts to reduce climate change through the reduction of GHG emissions, and also to reduce their current concentration in the atmosphere. But if funding goes towards both of these efforts in very decentralized and fragmented ways, it does leave out the consideration for these large transboundary environmental systems, such as the ocean, that have such a massive role to play in protecting communities just as much as protecting the planet. So with this lack of funding to taking care of these large systems of Earth's natural climate balancing, oh my gosh, sorry, so late in the day I'm losing my words, but with the lack of funding to protect these large Earth-based climate managing systems, we often find that there is nothing, or there are lack of efforts to protect and regenerate and repair these systems. And with this in mind, I'd just like to conclude by saying, if we are developing technologies, as we are, and if we are to develop it at the scale that's absolutely needed, as previously pointed by the panelists, we need to consider what's the role that developing countries and least developed countries can play in the development of these technologies. When we see countries that getting left behind because of lack of financing, lack of skills in that specific area, or even just a lack of being at the right table at the right time, we see that technologies are developed in a way that cannot be applied or scaled at the scale we need to see in order to protect the ocean. With that, I'd like to say thanks again for listening to me and pass this on to Shaun.
Thanks. Okay, last but not least, Shaun.
So, good afternoon. My name is Shaun Fitzgerald. I'm also with the Centre for Climate Repair. The Centre for Climate Repair is part of the University of Cambridge within the auspices of Cambridge Zero. Cambridge Zero is the University of Cambridge's climate change initiative, and it looks after the coordination of multidisciplinary, multi-institutional research programs covering climate science, adaptation and mitigation. And obviously we're here to talk about ocean-based carbon dioxide removal. I did just want to reflect on one question that had been posed to me a number of times over the last week, which is this challenge about the role of carbon dioxide removal and yet this incredible need to reduce emissions. And should we even be talking about carbon dioxide removal when, frankly, we're making paltry efforts in our progress towards emissions reduction? And the reason I feel quite strongly about carbon dioxide removal is that there is clearly a clean-up act that we need to sort out. That's to basically undo the damage and reduce carbon dioxide levels from their current level to an acceptable one. But going forwards, if we want to be truly equitable and inclusive, we need to think about other societies. And the story that I was challenged with, a neighbour of mine, grew up in Africa. And he said, Shaun, You know, people are talking about sort of, we should not be eating beef, we should not be having animals, we should be eating a plant-based diet. Well, that might be true in jolly old Cambridge, but in Africa, you can't actually grow the crops, the arable crops, and their source of protein has been for many, many, many years, has been meat. And therefore, the idea that we should bestow our solutions and thinking onto these other communities is something that needs to be highly questioned. And therefore, we need to think very carefully about even telling people that they should not eat meat, right, worldwide. So there will be a role for carbon dioxide removal in what we call the net part of net zero, to just trying to counterbalance the emissions that will go on hereafter. And clearly agriculture itself has got lots of emissions associated with it. So we need, clearly, environmentally safe, socially acceptable and economically viable carbon dioxide approaches, and they're needed to support certainly the realisation of worldwide climate policies, but arguably also within Europe, because there are going to be certain processes that we cannot easily decarbonise. Now, the reason I get excited about the ocean is that if I just look at the land, and we've got lots of nature-based solutions and maybe land-based solutions which take energy and then convert that into sort of fans to go and drive direct air capture. Look, the amount of land area that we have available, we know that the ocean is 2/3 of the world's surface, and therefore this as an opportunity to get that exchange of carbon dioxide out of the atmosphere into the oceans. So from just a rational scientific point of view, that's what drew me to the oceans. But answer first is that actually, if we're going to look at the oceans, we must not look at the role of the oceans just with carbon dioxide alone. It needs to be looked at in a more holistic fashion, as Alil, for example, has just explained. We need to be thinking about the communities that live and draw upon the ocean in order to even survive, but also the ecosystems that are within those bodies as well. Now, as Kerry mentioned, there are lots of knowledge gaps, and I'm not going to repeat those, but there are lots of knowledge gaps in marine-based or ocean-based carbon dioxide removal, which have been documented by others. And the challenge we've got right now is how to fill those knowledge gaps as best we can. And if we want to say we want to fill those perfectly before we do anything, that will be the quickest way to going nowhere. We need to think very carefully about trying to navigate this path of filling this knowledge base to a certain sufficient level, and it's about managing risks. Because at the moment, as we've just heard, the risk of not doing anything is huge, and we've got to figure out how that compares with the risks of trying to work with the oceans as an opportunity set. So, in order to do that, we need to look at the requirements for safe implementation. In other words, is what we're going to do going to make the oceans even more acidic, even more devoid of life? Are we going to really hurt them? So that's the first question about safe, as well as with people, in terms of the safety factor, and then clearly being effective. And this has got some very large challenges associated with it in terms of knowing whether you have actually decided on a given approach that seems to be sort of promising. How will you know that it is going to be effective, and in which parts of the ocean? Very big questions. In the IPCC AR6, Working Group 1, there was a lovely table that was introduced in 2021, which looked at the characteristics of carbon dioxide removal. And I've put in a blue box here, the ocean-based or marine-based carbon dioxide removal approaches that were highlighted there. And with the project CO2 CDR, which I will mention at the very end, what we're looking at is this as a guiding sort of help, really, for understanding what would need to be true in order for a given approach to be used to be safe, recognizing the different characteristics that they have and the work that needs to be done to further our knowledge base on each of those. So the first thing is a recognition that there's only so far that you can go with modeling alone. And Kerry made this really clear. There will need to be, at some point, in situ marine scientific research. There will need to be field-scale experiments. There's only so much you can do either with a computer model or just with laboratory experiments. So how do we do that? Well, that's not easy. We need small-scale controlled field trials in a range of parts of the ocean, and these are going to be required to evaluate the efficacy, impacts, and the operational requirements of ocean-based carbon dioxide removal approaches under real-world conditions. And actually, in some cases, this is learning about the challenges of working in the marine environment. You know, you're trying to do something and you can't do anything for 6 weeks or even longer than that as a result of weather conditions or something like that. So it's really important. The research has to be precautionary. And as we've heard from Alil and others, it needs to be really inclusive. And actually, if I had a vision, much of this work on ocean-based carbon dioxide removal would not be led by the global north. It should be would have projects being led by the global south, as well as those perhaps being led by the global north. But every project itself should be completely inclusive. And it obviously needs to be well planned to avoid harm to both the environment and indeed social systems. And then it goes without saying that anything you do, research, and certainly thinking about future deployment, needs to be compliant with the regulatory systems that are currently in place. One of the challenges that we do have is understanding how on earth will you know whether you have not damaged something and whether what you've done is effective. Now, this requires robust monitoring, reporting, and verification, but not just in terms of carbon dioxide removal. It requires robust monitoring, reporting, and verification on other aspects of the ecosystems as well. They need to be cost and climatically effective observational capabilities, spanning, ideally from the seafloor, actually into the atmosphere. Certainly, we're going to need to get very different types of equipment at play in order to get a full understanding of what would happen if you were to pursue a given approach. And those initial field trials should ideally over-egg it. We should be trying to monitor things that we might not think are important, because it's only by overdoing your initial measurements can you actually get a better understanding of what might be required going forwards if anyone were ever to use these as potential approaches at a larger scale. So we have to overdo the measuring to start with. And then as we go forwards, we should reevaluate and continuously learn to see whether we can refine our MRV approaches going forwards. And then in terms of effective implementation, it's going to be clear that not all ocean-based carbon dioxide approaches can be or should be applied across the whole ocean. So we need to have a more nuanced, more refined understanding of the carbon dioxide removal potential of different approaches, and these will draw on findings of pilot studies and by engaging with relevant stakeholders and communities. And what's really important is that we don't just look at a given approach, but we look at the full supply chain or the value chain, so we understand what the carbon impact is. For example, if looking at things like ocean alkalinity enhancement, go and look at the full supply chain of what would be required in terms of the gigatons of material that you might consider adding to the ocean. What does that do at the high end, the back end, in terms of where the mining took place? The whole lot. We need to make sure we have a better understanding of the whole process. And that scale will only happen, in the reality, is if they're economically viable. So it's incredibly important to have businesses involved at the early stage as part of the research. And then, as always, with any actually research program, but certainly ones on the oceans, we need to make sure that we have really equitable governance structures, which means the full range of stakeholders being incredibly inclusive. And when we talk about data accessibility, reporting mechanisms should be adhered to the FAIR principles. That's findable, accessible, interoperable, and repeatable. It means by everybody, not just by those who've got access to particular systems. It needs to be that they are really accessible by all. And there are some thinkings going on at the moment by the London Protocol, London Convention parties, looking at options for appropriate action for some of the approaches. And then lastly, what we need is good communication, transparency across the whole raft of the activities going on in this field. And where we hear people who are doing things and not sharing their data, that should raise alarm bells. We need to make sure that we're being completely disclosing everything, warts and all, experiments that didn't work, things that we found that we didn't like, being really, really open about this, because this is the furtherance of knowledge for society at large. And the last thing I wanted to mention is the CO2 project, which Ed mentioned at the very beginning, is that this is a €7 million funded project by Horizon Europe, drawing upon a number of 14 partner institutions across Europe. But importantly, we're interacting with and being led by Chris Pearce at the National Oceanography Centre, also interacting with people outside of Europe. For example, we've got people from the United States here, and it's really, really important that we engage with stakeholders in the global south. So we're working with partners in Namibia at the moment, learning from Kelp Blue, Kelp Forest Foundation. That's just but one example of we need to make sure that we're learning from them. They're teaching us, about what's going on, and then actually if we've got something to teach them, that might be nice too. But it's a really inclusive way of undertaking research. And with that, I think I'm going to hand the floor back to Paul.
Great, thank you, Shaun. And that was a great way to wrap up the presentation side of this. We've got about 25 minutes or so for some discussions. So just to kind of put put a little context on that, and then we'll see if there's questions from the floor. And there's certainly things that we're all happy to discuss amongst ourselves. We're really creating now a very new community of practice across disciplines, across sectors on this very new and emerging, rapidly emerging field of ocean carbon sequestration, marine carbon sequestration. And I just really wanted to emphasize this where we're at on this. Things are moving so quickly, but at the same time, we've got the need for answering these important research, fundamental research questions. If those of you familiar with the book and the terminology, speed and scale, I mean, we're in this climate crisis. We've got to move quickly. We've got to move at scale, and yet we've got here our largest our largest ecosystem, our largest nature-based solution opportunity for carbon sequestration is the ocean, but we've got some fundamental research questions that need to be worked on at the same time. And on our side at the World Ocean Council, we've got these great enterprises that are developing, that are working to, and they are starting to deploy prototypes in the field, in the water, and so these things are moving rapidly, and we've got to coordinate and harmonize this and have the policy and regulatory environment and conditions emerge at the same time. So there's a lot of moving parts for something of planetary significance, and speed and scale is important. We collectively, the planet cannot wait to get everything set up first, and then we start implementing. We've got to really coordinate all of this and advance it. So with that sort of sense of the moving parts here and the big picture and the big stakes here, the risk and reward versus, the risk and benefit kind of balance here, are there questions, thoughts from the audience? Catherine. And if people could introduce themselves and their affiliation, and really a sharp, concise question to put to this great group that we've got up here.
Thank you, Paul. My name is Catherine Chabot. I'm from the European Parliament. And we know each other because I co-founded the Ocean and Climate Platform 10 years ago. And in the Parliament, I'm trying to push all ocean issues. And I'm trying to highlight the blue carbon since 4 years, trying to put it in our European legislation, climate legislation. Thank you very much, because for me it was very interesting to listen to you, because there's a lot of questions, challenges, as you said, and I will have a question because for me there's something missing in the presentation, but I'm not an expert. First of all, to highlight that I am in 3 committees in the Parliament: environment, fisheries, and development as well. I've been twice. I had 2 or 3 missions in Senegal and Guinea-Bissau, etc. I've been visited communities in the mangroves, etc. And I think there is we need, because we always put the ocean topics in silos, and we really need to have an integrated approach. And we know today that if we want to restore mangroves, all the blue carbons ecosystems, we need to address the pollution problems on land, plastic and water pollutions as well. And I would like to know if you're in your presentations and in the evaluation, economic evaluation, if you, in the co-benefits or the impact transfer, do you take into account those benefits that you should have on land, if you understand what I mean? And I think you put all those, the several solutions at the same level, but for me, but I'm not an expert, so that's why I'm here. it's very interesting. I feel, I have the sentiment, the feeling that solutions, ocean-based, ecosystem-based solutions are very useful for population, for everything, and also for economy. But what about iron fertilization, electrochemistry, etc., geoengineering, that will cost a lot of money do you have co-benefits on those solutions? You understand what I mean? You put all those solutions at the same level. For me, they are not exactly at the same level. And I think, yeah, do you follow this life cycle approach that we need to have? Thank you very much. And I think it's very important to begin to think about those solutions when we see the draft GST of the COP28. Probably we will have to find solution with the ocean, but what solutions? Sorry.
Thanks. Catherine, who wants to jump in on that?
Well, I'll start. So the CO2 CDR project is but one of the research projects funded by Horizon Europe. So it was on greenhouse gas removal, and there were 3 projects funded, and there's also another one funded by the United Kingdom. The one in the United Kingdom is looking mainly at land-based carbon dioxide removals. And what's really important is that the CO2 CDR project, the ultimate purpose is to try and develop a framework by which different ocean-based carbon dioxide removal approaches can be compared and evaluated, which looks at the full life cycle, but the project itself is not doing a detailed furtherance of research of all of these different approaches. That would be a big ask for 7 million euros. It's developing a framework by which they might all be compared. But the critical thing is also linking up with the other projects that are looking at, for example, land-based, and also looking, for example, at projects that are also considering on the land reduced emissions, which will therefore, for example, one way of doing that is reducing the use of fertilizer and therefore the reduced runoff and then the impact on the ocean. So it's important that these different, you're completely right that it's quite siloed, but what's really important is that the different project leads are then in communication, and that is part of the plan, and that's what Chris Pearce, who can't be here, but he's the principal investigator for that. So that's the answer to that first part of the question. May I hand over to somebody else to answer the rest of it? They've heard enough of my voice.
Yeah, I'll answer a little bit to some of the potential co-benefits of the technologies, but I just want to emphasize too that I think the research is still a little too early to know the full extent of some of the potential of the co-benefits. So for example, growing macroalgae for carbon dioxide removal, there is the potential for where that algae is located, if it is co-located, for example, with other aquaculture operations, that it can actually improve the water quality. And my background is actually as an oceanographer and marine ecologist, and I used to do studies to look at kelp forests and how they change the chemistry of the water. And you can see some really significant signals of increased oxygen and increased pH, like where the macroalgae is, especially where the most of the biomass is, which needs to be towards the surface where there's enough light. So there are some sort of potential co-benefits there. There's also with the macroalgae the possibility of growing that macroalgae offshore and then using that macroalgae for low carbon products. But that's something that people need to think about. What do those products look like? What is the life cycle of those products, et cetera? As far as the electrochemical method, there's one group that's looking into it that was speaking yesterday. I cannot remember. Aquatic, I think.
Aquatic, yeah.
There, with the electrochemical method, they were discussing the possibility that green hydrogen would be a byproduct of that could be useful. And then one other example might be with ocean alkalinity enhancement. There are some areas of the ocean where we're already experiencing some pretty severe ocean acidification. And so I know from, I think even from an ecological restoration perspective, the idea of, enhancing some of those ocean areas with alkalinity is also attractive for decreasing ocean acidification. So just a few examples of some of the potential co-benefits. But again, there's also risks, and so we need to do more research.
Maybe another thing to point to, you saw the covers of many reports, at least in the Academy's report, we tried to look at all 6 and then in a series of tables. It's 300 pages, you don't have to read the whole thing, but there are summary tables like all of these high degree confidence, low degree confidence, and looking at things like state of knowledge, the cost, the scalability, the durability, the social barriers. We went through 12 people over a course of a year and a half and tried to put that into context. And there are some big difference. One thing I found kind of astounding, having worked in the iron field longer, is know a lot more about that. We've done experiments. We haven't caused permanent harm. We know some numbers for how much was removed. What seems to be interesting to me in the commercial side, it's what we know the least about that's generated a lot of interest. And these things that maybe are more tried and true. We're saying, well, I'm not sure that's very good. Let's do alkaline. We've never done that before. And I think we have to watch out. And so the conclusion of the group was we need to be, learning by doing, getting these things in the field, but some of them are already basically shovel ready to go. We've done those experiments, but in some of these cases, we've never ground up minerals to look at toxicity to algae, things like that. New work that's just coming out. And so there are some important differences. Cost-wise, the nature-based ones are typically cheaper because you're not buying energy from some source or getting energy or building factories or things. So yeah, all of those things need to be considered, and I wouldn't want to rule anyone out right now. I think it's too early.
So I think, Catherine, a great question, a whole lot of pieces to that. I think, getting, at some point, working with you to have a briefing to the interested individuals in the European Parliament on ocean CDR would be great. So I think to work towards that. Other questions over here? And I'll just add in a little piece from that one point that you brought up, Catherine, before we have the next question, about that I picked out. You had so many interesting pieces to that, was the pollution aspect in the sense that a co-benefit or an aspect of any kind of ocean or marine carbon sequestration is that, and this is where the research could help us really articulate this, to the extent that a healthy functioning ecosystem is critical to achieving the numbers of sequestration that we want, and so therefore it pushes further the need to reduce pollution or anthropogenic impacts to that marine ecosystem. And we've got this carbon and this carbon driver for reducing pollution as an additional kind of incentive to get this right.
Hi everyone, I'm Emily. I graduated from Xiamen University studying marine oceanography. I'm now at Yale University doing research on salt marsh blue carbon and also freshwater. So coming from an oceanography background, now doing freshwater ecology, our lab is doing like enhanced weathering, but people stop thinking after what goes into the ocean. Once it's in the river, that's all they think about. So I'm just wondering, because there is enhanced weathering on land and also ocean alkalinity experiment on the ocean, like do these people communicate with each other? And there is only so much funding, like when comparing these two projects, what are some of the syndromes you face and how do you, answer to those?
Thank you. Who wants to jump in on that?
So I'll keep the answer short. It's a great question. I'm encouraged to be able to say that my experience is that they do talk, and in fact some of the same individuals are working on both, which does aid the communication somewhat. But no, it's a really, really important point, and but I have seen there's stuff going on certainly in the UK that I'm aware of, and I sincerely hope that it's going on elsewhere as well. And I should ask Chris, who I know is looking at this.
Another example out of Woods Hole Oceanographic Institution, Adam Shubash and Alec Wang, I look at the impact of the Mississippi River in terms of the alkalinity additions into the Gulf of Mexico, because they weren't ready yet for experiments, but there's this natural experiment, alkalinity being delivered by these major rivers. So yes, that does happen. And using natural events in iron, we look at things like volcanic eruptions, forest fires delivering things. So that's another way to make the connection to these land-based sources that ultimately affect these ocean ecosystems.
Other comments on that? Other questions from the audience? Yep.
Hold on, that microphone isn't working at the moment. There it is.
Sorry about that. Alan Evans from the National Oceanography Centre in the UK. There's a little bit of tension at the minute between the researchers needing to understand the impacts of CDR and the industry wanting to plough ahead and do this. How realistic is it, taking into account the spectrum of potential CDR technologies, how realistic is it that those technologies can be upscaled to make any meaningful contribution to global CDR?
Here I can maybe start. I mean, I think that a really important piece here is collaboration between all of the different groups, so including industry as well as, academic institutions and also public agencies. And so here, maybe we can highlight this really cool program that the U.S. National Oceanographic and Atmospheric Administration has a program, the NOP program, it's National Oceanographic Partnership Program. And the goal of that program is to bring together different entities to collaborate on projects, to do the science as well as to advance, the knowledge to further the industry. And so there's really great collaborations going on. So you have to have at least, I think, 3 different partners that have to come from agencies, like public agencies, academic institutions, industry, or an NGO, and you have to have like 3 out of the 4 in order to be eligible for this pot of money to move forward. And then I'll also highlight a program that we have within Ocean Visions, which is called Launchpad, which different startups apply to the program, and then we connect them with scientific experts so that they can get very specific feedback to their specific technology that they're developing, their engineering concerns, like things like thinking about site suitability analyses, to really try to make sure that, as the companies are moving forward, that they have access to really great scientific expertise to further, just to make sure that they're moving forward in the best way possible.
In terms of the scaling numbers, you asked about billions of tons per year. When we looked at the 6, 4 of those could get to the billion-ton per year level, single billion. So get 4 gigatons there. The other 2, you're up to about 5. You're getting closer. Some of the engineered ones you can scale even bigger, but we might not want to. It might be too difficult, say, for alkaline enhancement to be adding more than 1 billion tons of rock a year or something like that. Others are a lot easier to scale. So when you start thinking about it, if someone's coming to you and say they have these solution, I think you should run away. It's going to take a lot of these at the same time to get to 5 or 10, not a single one. And none of these, at least I believe, have the scale, and I don't think anyone does, to get up to the 40 billion. This is not a replacement for emissions reduction. That's why you heard that several times. So that's been a critique, a moral hazard issue that we want to always keep in front and center.
I'd like to ask Eleni, if from your work on technology development, how does that do you see a connection here in terms of the technologies emerging from the industry side and how that relates to responding to Alan's point about can these technologies provide the scalability that we're after or that we need for carbon sequestration?
Definitely, in order to scale to any type of meaningful level, of course, not reaching the full extent needed, we absolutely need to make sure that there are people from around the world who are participating in this. We need to be able to optimize the use of oceans and coastlines in order to implement these technologies. To add another perspective, there's also an intense motivation to research and understand these technologies. If you consider, for example, where I'm from, 10 years from now, it won't be possible to work outside for more than like 4 hours a day. So you can just imagine the impact that'll have on my economy back home. There is an intense motivation in the developing and least developed worlds to understand this technology and play a part in the development and scaling of it. But there are still a lot of challenges. One, in terms of research capacity, there's a very stark gap between the way the world's in the global south research and the way that research is conducted in the global north. There's also a gap in terms of the types of pioneers, industry pioneers that exist, who are also clustered generally in the global north. And then there's also the case of financing. How do developing countries that have to prioritize between education and food security find budgetary space to invest in research and development of these types of crucial technologies. So there are certainly many challenges, and these are just some of them. But I think in order to make sure that we are able to optimize the use of the oceans, we need to make sure that we're able to bring all people to the table, assess all viable options, and then find the most suitable, most ethical, and safest ones for all people affected.
Okay, are there any other, we've got a few more minutes. Did, Shaun, had you wanted to jump in on that one as well?
Just very briefly. I mean, so the road mapping exercise that Ken and Kerry and is being done by CO2 CDR, it's not just the full potential, in other words, the gigatons, it's actually the time scale that will be, that will have to unfold in order to get to that full potential. That is included in the evaluation of these different, and the comparison of these different approaches.
I think, I'd like to just, we've got a few more minutes to just a bit of interaction amongst the panel here. This context of developing and getting the support for the research program while we've got these enterprises, these businesses getting underway. We really are going to have a clear, there's a lot of nuance to this, how we're going to move forward with all of these things all at once. I'm just really interested in some of your perspectives on how we do this. And the short answer would be, let's just wait and do the research, get a lot of that work done and put everything else on hold. I think there'd be, well, maybe there's not, agreement that we can't just do the research over the next decade. We've got to allow the potential for the scalability to move forward from the companies, kind of related to Alan's question. At the same time, how are we going to communicate this well? That the world can't just wait for the research to come in before we can start edging into the business and commercial and investment viability here.
I mean, I guess sort of, building off maybe my previous answer is actually more appropriate for this question, but I think by having these partnerships and working collectively, sharing data, I understand that there's some, concerns with companies about what data they can share because of IP concerns, but, really trying to move the field forward together and use any information that's collected by, any company to also feed into the science, and with the, with these businesses and industry partnering again with nonprofits, with academic institutions, and with public agencies.
And just a bit of this context is about what's the common research agenda so that we can ensure people that there is this good working relationship in a transparent way between industry and the science community. And so maybe others have thoughts on that's part of the context, I think, as well. And we had a good chat about that after this morning's session.
I feel quite strongly about this, and it's about the principles that are at stake. So it's not about necessarily who's funding, it's about the principles behind that agency or that entity that's doing the funding. And are they prepared to be, clear and transparent, fully inclusive, to share with these things? And if that's government, if that's trusts and foundations, whether it's philanthropists, whether it's businesses, actually it comes down to the fundamental principles that are at stake. And we made that hopefully reasonably clear that, we want to be completely open and transparent. Now, as it turns out, what are the sorts of things that you might not be, prepared to share? And that goes on with every organization. For example, individual salaries of people, except for the very top. That's not the sort of stuff that gets shared. So it's not that you have to share absolutely everything, because we would never do so in an academic institution. But when it comes down to the integrity of the research program, about sort of what's at stake regarding a future approach for carbon dioxide removal, then that's where we're going to be very clear about the sort of the level of transparency that we're looking for, Paul.
And these codes of conduct that we've been setting up, I think it's important that we ask them to lay out what is their code, how are they doing this in these open and transparent ways too. I think that's going to be really important, and to get permission to use. In many of these cases, we're talking about open ocean. Who owns the open ocean? Where's the rights to use that? Well, under the London Protocols, they will not allow a commercial enterprise. This is being allowed for, under the permitting process, academic research. And so not academic research, I should say. And so that's going to be a limit. So if you're getting carbon credits, I think that would put the kibosh on that. Now, people can go around those rules, bad behavior. We're going to see that, right? This is going to be $1 trillion economy, 1 billion times 100 times 10 tons. That's some target. We're going to see a lot of bad behavior. We're seeing a little bit already, let's be honest. But I think we have to lead by example and, you know, support those international rules that are out there, even if they're not signed off by every country. I'm in a country that doesn't sign those agreements, but that's how we want to move forward as academic scientists.
Yeah, yeah. Thanks, Ken. I think that's a good segue into
Great.
having Ed pick up here with our closing remarks as we wrap this up. Thank you all for being here with us. So, Ed.
Great. Thank you very much, Paul, and to all of the panelists. So we've heard that the IPCC Sixth Assessment Report has said that there's no pathway to the Paris targets that doesn't involve some level of carbon dioxide removal. And we've heard also about the way in which scoping studies such as the US National Academies, the Ocean Visions roadmaps is helping to inform further work. Some of the approaches, like restoring coastal ecosystems, the co-benefits are obvious, but they have constrained scalability. For other approaches, like altering ocean chemistry, there's much more scope for deployment at scale, but there are other questions about the net benefits and the ecological impacts. And they invoke stronger opinions, both for and against. Independent and inclusive science, we've heard, is absolutely crucial and needs to lead the growing interest in debate that's now shaping up in this area. And that's why we're especially pleased to have had the opportunity to bring the discussions of MCDR to COP28 to help broaden the engagement in this very important conversation. There are many technical questions that need to be urgently addressed around many of the CDR approaches, but we've also heard that it's unlikely that any one single approach is likely to be the answer. There will be different approaches that are more effective in different settings and scales. The technical questions include the efficacy, the scalability, the durability of sequestration, ecological impacts, looking at the whole life cycle, carbon benefits, and the whole monitoring, reporting, and verification. But the science needs to lead to reduce the uncertainties and eliminate rapidly the non-viable options so that we don't waste time in nugatory effort. What is needed from a scientific point of view are laboratory experiments, small-scale field trials, and modelling both at local and at whole Earth system scale, with the results openly available and transparently accessible. We need to be open to the outcomes of the science, some of which may demonstrate that, all things considered, some MCDR solutions are viable or not. The research needs to be impartial, we've heard, without fear or favour, to the many voices and interests that are involved, often arguing passionately and with conviction, emphasising different issues, from the moral imperative to act quickly, through to frustration with current emissions reductions rates, through to the opportunities of an emerging ocean economy sector in this area, as well as concern for unintended ecological and social impacts. So this is a space where scientists need to be right in the middle of it and to navigate with objectivity and with scientific integrity. For example, a very strong sense of urgency is framing the considerations around MCDR, but this is no reason to suspend or dilute accepted scientific standards of rigour, including peer review and openly accessible data. This is integral to the scientific method, and this has stood the test of time. It's also important, too, that disproportionately applied regulatory barriers don't needlessly hinder the very research that aims to test the viability or otherwise of MCDR approaches. And so alongside these questions of the technical questions around the workings of MCDR, there are a whole set, we've heard, of complex social, economic, engineering, legal and governance issues. The whole question of the ability of developing countries to adopt these technologies, and the inclusiveness and participation of societies who will be affected by them and could benefit from them. So impartial, rigorous science needs to be in the thick of these types of issues about which there are strong opinions. These matters are sometimes contentious, but they're contentious because they're important. And if they're important, then science needs to be right there in the middle of it, ensuring it's informed by the best available data and evidence. So I'd like to thank all of today's panelists for their insights to this important and timely issue, which has been a major theme running through the conversations around COP28. They've been prominent in the Ocean Pavilion in particular, but elsewhere too. And I'd like to thank you who've joined us in person or online for your participation. So thank you all very much.
Yes, great idea.